All right, so first I'll start with a funny story. It's only been like I'm only 4 minutes late, but we have time for a story. So, parenting, woo. Um, so after the second time I texted my wife to inform her that her baby was in fact an asshole, I followed it up by doing a quick Google Map search for nearest fire stations and then sending her that map. No other explanation, just sending her a map of fire stations. And she said, "Are you sending me this because you're implying you're going to drop him off at a fire station?" And my response was simply, "Yes, I'm going to drop him off at a fire station." I did not, but I was close. I was like, "Oh, baby." He was in rare form. She's like, "He's just too tired." I'm like, "Well, he should go to sleep." He did not go to sleep. He's like, "I don't want to go to sleep. I hate you." And I was like, "Oh, interesting. Interesting stand, baby. Interesting stand." What? It's probably, it was really up there with me for me too. It was almost my worst day ever, and I've had cancer. So like, I'm like, oh man, can I get cancer again if you'll go to sleep? Like, come on, baby. All right. So in the realm of not sharing the screen with Zoom, I had enough problems, and I forgot to share the screen with Zoom. Way to go! Boom, Zoom. Boom. Zoom should have a screen though. How could you make that? I do believe this can take 2 steps, and Organic 2 will be involved for at least one of them. Now, also, I could probably think of a bunch of different ways to do this. But how could you put that double bond? Ow, as I hit my head on the screen again. See, you miss Zoom, you miss me like concussing myself. Oops, sorry. I seem to have lost the screen. What happened there? Sorry, Zoom. I got super old today apparently. There we go. Hopefully now Zoom can see a screen. I don't know what happened to my little thing, but nothing's working right today. So how would we make that? Okay. Sorry, Zoom. Give her back. Cool. I got my little thing back. Okay. So, right, let's think about. Do you have anything in chat? I do not. I don't think. Okay. So we talked a lot about ways of adding double bonds to things, right? And one way we could do this is if we had gone back to. Let's get the whole thing. What if we had a halide there? How could you go from the halide to that double bond? Right? Like I'll even let you buy the double bond. right? So like we could do some sort of palladium cross coupling, right? So if we could get to this bromide, we could go in the forward direction. We could say, hey, I have my double bond with a metal, let's say a boronic acid, and I would need palladium 0 and like a hydroxide base. I would need those things, right, if I had the halide. Now, we'll like clean this up in a second, right? And I can get from benzaldehyde to that bromide using the power of organic 2, right? So in the forward sense, you could say, okay, I need more space instead of writing right in the middle of the page. I could add the bromine. Should take like Br2 and FeBr3, right? That adds the bromide meta because an aldehyde is an electron withdrawing group that directs meta, right? And then you would just take, again, I went boronic acid, I went Suzuki coupling. You could do a tin and go Stille coupling. So you could take a boronic acid, and palladium 0 and some hydroxide base, and that would give you your product. What about taking your benzaldehyde and turning it into phenyl acetaldehyde? So just moving that double bond, adding an extra carbon, adding a CH2 between. You also heard the knocking? Okay. There's just a random knock in the room, and then the door closed. This building's not old enough to be haunted, I don't think, but still spooky. So there's one way that I definitely know you should be able to think of how to do this, and there's another way that I'm going to show you that is something I haven't shown you yet. But how could I get go from that aldehyde to a different aldehyde? How did we make aldehydes again in organic 2? Or sorry, organic 1. This is an organic 1 reaction. It involves everyone's favorite mechanism, or at least long mechanism from organic 1. It involves a sweet, sweet boron. Poor Alphonse is the only one here, and he shows a lot of pressure to come up with stuff.
Feel a lot of pressure, and it's like really upsetting because I can remember like the page in MacroChem notes,
Right?
the mechanism on it, but I don't remember enough of the.
Remember, if we have an alkyne and you do a hydroboration, that will make 1, 2, 3, 1, 2, 3. That will make an aldehyde from a terminal alkyne. So if we remember this, right, So now the question becomes, how do I turn that aldehyde into a terminal alkyne? This is great. I knew I wasn't going to need a bunch of slides this week because I had like 5 more of these to finish. Put it in red. Don't forget your test is Tuesday. They'll give you the take-home exam on Tuesday. Probably post it on Moodle. And then you'll have until Thursday to get it done. You'll have to somehow get me something. Okay. It was a name reaction. It was a funny name. Corey Fuchs. I can't remember if there's an E or not. Fuchs? Fuchsi's? I don't know. Right, so you can take an aldehyde, treat it with triphenylphosphine, and carbon tetrabromide, and then N-butyllithium, and that will make an alkyne. I went over that when I went over the panic synthesis of discodermalide. I do believe it was the panic synthesis. Right, and then I can hydroborate that. So then I can use BH3, and then H2O2, hydroxide, and water. I did the order differently. It doesn't matter as long as all that stuff's there. And that'll get you to your aldehyde. So another way that you could do this, that like I hadn't shown you until now, so like no worries, is you can do a Wittig reaction. You make a vinyl ether. So let's say we had aldehyde, and then you use, this ylide that has a methoxy group on the end. That will make do you believe it's cis? That double bond. You treat that with acid and water. That will become an aldehyde. So that's not fair. I hadn't shown you that before. But I should, the other one you should have. Mine like a steel trap. You should remember that one. All right. Benzaldehyde. We did the trans one last time. How can we make the cis one? what is the easiest way to make a cis double bond? Wittig reaction, right? So we could say, hey, this is going to be my Wittig reagent, right? So that would just require you to take PPH3, right? So if you see a cis double bond, one of your first thoughts should be, can I do this with a Wittig reagent? Because that's usually where they come from. You can get them other ways as well, but cis double bond, you should, especially if there's an aldehyde involved, you should think Wittig. That one was easy. All right, and then we've got, oops, no space. Our aldehyde. And we'll just add an alkyne and another aromatic ring. So we just saw how we can put an alkyne onto our aromatic ring, right, from our benzaldehyde. Right, we can Corey-Fuchs it up. I should be fair, then H plus, or then H2O. Right, to get the hydrogen on the end. And then how can I add an aromatic ring to an alkyne? So it has a redrive. How would it get from there to there? It's a terminal alkyne, so that makes life easier. Hopefully feverishly flipping through notes. You can quench it with something. You can quench them with something other than water, but you're not going to be able to add an aromatic ring. So we saw where you could go, right? You get to that reactive acetylide, right? Oops, that's a really bad lithium, right? And people added things like DMF to put an aldehyde on the end, or they added, say, like TMS chloride to put a silicon on the end. But there's not a good electrophile that adds an aromatic ring. So I'm not like trying to be like super tricky. You can do it from just the terminal alkyne. And it's a reaction we went over way back in the palladium cross-coupling stuff, where you take an alkyne and you treat it with copper and base. Yeah, trying to get you a reaction, right? So you treat this with copper iodide, some amine base, say triethylamine, palladium 0 of some sort, and then a halide. Right, so you'll put the copper on the end of the alkyne, and then that will be your metal for your palladium reaction. That's where your palladium 2 will do a transmetallation. Will be there. Oops. So that was a little review of kind of all the stuff that we hopefully know. Hopefully. Oops, hey, bring my window back. Sorry, guys. There, your window is back. Did I lose it again? This is so weird. Like Zoom is like acting totally different than it normally does. It's great. All right, so what I wanted to do now, hopefully, if it wants to work, is, of course it doesn't work. Great. Yeah, Zoom is acting super weird today. Like super weird. There you go. See if you want to. So we're gonna try this again. I'm gonna try to share this again. Then I'm going to. Nope. Trying to get the slides, but of course it doesn't want to be nothing easy, as it were. Oh, no, come back. Sigh. Why is it over there now? Over here. There we go. That's the problem. Okay. Resume share. Stop share. There we go. Haha. Old man has figured out basic technology. No, old man has not. Ha. Does Zoom see a slide now? Did we get there after like 20 minutes of me being dumb? Awesome. Okay. So, we did a bunch of ways to make double bonds, right? Either through like palladium, or we went through like Wittigs and Hornewasser Emmets and stuff. But we need to like use them for something, right? And kind of the basic thing that you can use a lot of double bonds for is you can do oxidations, right? You can add 1 or 2 oxygens, right? We saw this with dihydroxylation in organic 1, right, where you use osmium tetroxide and you'll add 2 oxygens to a double bond, or you use cold dilute KMNO4 and add 2 oxygens to a double bond, or hydroboration and you add 1 oxygen to a double bond, or epoxidation with MZPVA and you can add 1 oxygen in a 3-membered ring. That's all well and good, but I wanted to focus on some of the ways that we can do this asymmetrically and install not only the oxygens or whatever group we're adding to the double bond, but also install stereocenters. So we can, definitively add an R chiral center or an S chiral center based on what reagent or what catalyst we use when we do the reaction. So this is going to be a little bit less like mechanism heavy than some of the stuff we've done before. A lot of this is just kind of going to be like, this is a thing you can do. Be aware that this is a reaction that can like occur. But I'm not going to get like into the nitty gritty on a lot of these for like actually how it works, because some of them are pretty complicated when you like factor in what's going on with the ligand and everything. But I did want to just like, again, especially for the project, right? You've got to like make the right enantiomer. So I can't go over everything, but if you know these things are out there, you can look for things like them or related to them and use them when you're working on the project. Which I guess this Thursday, I've got 2 groups for sure. Team Remote Access, featuring Jonah and Corey. And I don't know what to call the Alexis Caitlin collab, but something. Alexlin or something. Right? And then I've got 6 free agents currently. So make a friend by Thursday. Okay, so just to remind you, there are 2 types of general additions to double bonds, right? There are syn additions, where the 2 groups that you add, whatever they are, come from the same side. And they're put on the double bond on the same side. So a lot of times this involves a reagent that is holding both of the groups and comes from the molecule and puts them on the molecule from the same side. So when you add, when you do a dihydroxylation, that reagent, the metal is holding both oxygens and then sticks them on the molecule from the same face. When you do a hydrogenation, a lot of times, palladium pulls hydrogen apart, holds on to both hydrogens from H2, and puts them on the molecule from the same side. Right? So the syn additions usually happen where both groups are being added simultaneously and being held onto by the reagent and being put on from the same side. Anti-additions, you end up with one group on one side of the molecule and one group on the other. So a lot of times this involves doing an initial addition to the double bond and then a second addition. So like the quintessential example of this is adding bromine to a double bond, right? So oh no, there's stuff there. Right, so the classic anti-addition is you have a double bond and you add Br2 and you end up with one bromine that is up and one bromine that is down, right? And if you remember, right, you have a situation where you add to one bromine and that bromine adds back to the double bond. And that Br minus that you made, minus, then adds, right? You add once, that bromine that you add the first time blocks the face of the double bond, and then you add a second time from the other side that is open, and that gets you your product. Right, so that's kind of the classic anti-addition. I feel like most of the asymmetric reactions are syn additions, and that is kind of because, right, it's easier to control the reaction when your reagent is coming from, when both things that you're adding are coming from the same thing. right? As opposed to having to try to control 2 additions, you only have to kind of control 1, right? So, because I was planning ahead, I even put examples in the slides. Look at me go, right? Right, so hydroboration, that is the syn addition. The hydrogen, and it's really the boron that you add because the boron turns into the OH, come from the same side. And then the Br2 example, those come from opposite sides, right? So when you saw these reactions before, we only cared about relative stereochemistry, right? We just cared that they were on the same side or opposite sides. We didn't care which group was up and which group was down. Now we should probably care which group is up and which group is down, right? We want to care what enantiomer we're making, right? So now we can control this. We can pick which enantiomer we're going to make kind of 2 ways. One, we can use chiral centers that are already in the molecule and use that chiral center to impart stereochemistry when we do our reaction. So we can use a chiral center that already exists to dictate which side of the double bond your reagent comes from. Or we can have a double bond and then use the reagent itself, put chirality on the reagent or on the catalyst, and have that chirality install the chirality on the reagent itself, install chirality into our product. So we can use chirality already in our starting material, or we can use chirality in the reagent to make the reaction work, or to install a chiral center, right? So I've kind of broken down that there are 3 ways that we usually will install chirality in one of these reactions. The first is allylic control. So this is using a chiral center that is already in your molecule to dictate where your reagent is going to approach your double bond from. Then there's coordination, where you've got some functional group that is Lewis basic that can somehow donate electrons or bind to your reagent and will hold your reagent from one side or the other. Usually these are oxygens or nitrogens, right? And then finally, there's using chiral reagents or chiral catalysts to install your stereochemistry. Right, and we're going to go through examples of all of these. For allylic control, I have to teach you actually how you can draw the right conformation of your molecule. And the other ones are a little more just like it works like this. Give everyone a second here. Okay, so there's some terms that I want to introduce just so when you see them on slides, they make sense. So there are 2 ways that we talk about a reaction being giving chirality. So there are ratios where we talk about the enantiomeric ratio, ER, which is the ratio of R to S, right? So it's like I have 90R, 10S. My ratio is 90-10, right? Diastereomeric ratio is I've got 90 of diastereomer A and 10 of diastereomer B, right? That's pretty straightforward. We usually use diastereomeric ratio way more than an enantiomeric ratio. So this is, again, right, right? So ratios. Right, 90, 10, that's your enantiomeric ratio. ER, right? And then you have your diastereomeric ratio, which when you have diastereomers, you have more options, right? Because of how many chiral centers you can have and whatnot. But let's say we just had this week be like 80 of this, 20 of this. So this is a diastereomeric ratio. Oops. I'm not gonna be able to fit that there. DR. Now this will oftentimes get like broken down to like the simplest possible like fraction or whatever. It'd be like this is 4-to-1. All right. So we usually use diastereomeric ratios way more than enantiomeric ratios. The thing we like with enantiomers is we like to use excess. All right. So we have. I'm going to switch back to our slides real quick. There we go. So excess is for enantiomers. You're going to see the term EE a lot. It's enantiomeric excess. You occasionally see DE, diastereomeric excess, right? And excesses are reported in percentages. And not that I'm going to have you do the math ever, but, oh, was that a 0? I'm sorry, that should be, let me fix that real quick. Sorry. Yep, screen is not being shared. I fat fingered that apparently. There you go. Okay. It is fixed, question mark. Is it doing the thing where it's moving it over there? Oh, wait, that's right, I can't do it. Wait. And I've got to go through the like rigmarole of sharing 2 screens to get to the screen I want to share. There we go. New share. Boop. Ha, we did it. Okay. So the formula is you take the amount of the R enantiomer and you subtract the amount of the S enantiomer from it, and then you divide that by R plus S. So, and then times 100 to get the percentage. So the higher your, so EE or excess is a kind of a much more stringent value, right? If you have something that is 90% EE, that means you basically have a 95-to-5 ratio of enantiomers, right? Because it's 95 minus 5 is 90 divided by 95 plus 5, 100, gets you to 90%. So when you see really high EE values, right, above 90, right, you basically are getting almost exclusively one enantiomer over the other, right? But you're going to see EEs usually in the neighborhood of, for like, simple reactions that are good, that are 95% EE and above. Right? At that point, you're getting, again, at 95%, it's 97 to 2, basically. So you usually see ratios for diastereomers and EEs for enantiomers. So when you see the term EE on something, that's what it's talking about, is how much more of one enantiomer did you make than the other, right? So for the first thing we're going to start with is we're going to start with allylic control, which is using chiral centers that are already in your molecule to dictate your stereochemistry. So when we're talking about allylic control, we're specifically talking about the chiral center that is at the allylic carbon to the double bond you're reacting with. So if you remember, he says hopefully, from, I do believe it's organic 1, right? When you have a double bond, these carbons here, we have blue arrows pointing to, these are your vinyl carbons, right? And then the carbon directly bonded to your vinyl carbon, this carbon right here, is an allylic carbon, right? So when I'm talking about allylic control, I'm talking about using chirality at that carbon to dictate how a reagent is going to approach your vinyl carbons, right? So there are two types of strain we need to worry about when we are talking about allylic carbons. And I'm going to draw them. I have like a little diagram, but it'll be easier, I think, if I draw them first, right? So there are two strains. There's A13 and A12. Now you've seen the term A13 before, right? And that was in 6-membered rings. A13 here means allylic 1,3 strain. Oops. So what we're looking at is we're looking at the group. We're looking at basically 1, 2, 3. Right? We're looking at the group on this vinyl carbon and its interactions with the groups on the allylic carbon, right? And then A12 strain is, again, allylic 1,2 strain. So A12, not 3, 2, is allylic 1,2 strain. And that is your double bond. And you're looking at now 1, 2, the interaction of the group on 1 on this carbon here, on this vinyl carbon, with the groups on the allylic carbon. So you're trying to minimize both A13 and A12 strain to in your starting material, and then use that model to determine if you're going to approach the double bond from the top face or the bottom face. All right. So I guess the thing that's kind of most I'm trying to think of if there's like a good analogy from like earlier classes. I don't think there is. So what we're looking at, right? We'll go over how to draw them in a sec. Is so if we have a double bond, if we have just a hydrogen on a double bond, so we have like a terminal double bond or a trans double bond, right? And we're basically going to say that here having this hydrogen inside, beside this this hydrogen, we're going to kind of set that as having like no strain, right? And we've minimized our A12 strain because the hydrogen here is in plane, and the two methyl groups here are above and below that hydrogen. So like if you were to draw a Newman projection, they'd look staggered, right? So you'd have your hydrogen here, hydrogen, and then your two methyl groups come around it, as opposed to being eclipsed, right? So then we have A13 strain, whereas we take one of the non-hydrogen groups and we put it in plane. So it's now basically eclipsing the hydrogen on the double bond, on the far carbon of the double bond. And that's your A13 strain, and that has about 0.7 kcals per mole, right? And then if we have it, so we have our two groups on either side, like staggered from the hydrogen on the double bond. It's the minimizing A13 strain, right? Now the A12 strain, where those two hydrogens eclipse each other, that has about over 2 kilocalories per mole. So the conformation that this molecule spends most of its time in is this conformation here, where these two hydrogens eclipse each other, but they're small and they're far away, right? They're 3 carbons apart. And then these two groups split or on either side of this hydrogen, right? So even they're closer, but they don't eclipse at all, right? And now when we have a methyl group or some carbon on our double bond, again, this is going to be our low energy conformation. It's not zero, but we're basically saying this is as good as we can get, right? Where our hydrogen, our smallest group, is beside this methyl group. And then our two groups on our allylic carbon are on either side of the hydrogen here. And then our A12 strain, where the two hydrogens clash, where they eclipse, is like 3 kilocalories or 3.5 kilocalories per mole. And the A12 strain, or A13 strain, where the two methyl groups are in plane and effectively eclipsing, that is over 4 kilocalories per mole. So I do believe the number is 1.57 kilocalories per mole. That is the amount of energy to get a 10-to-1 ratio of something. So if there's a difference of 1.57 kilocalories per mole, I think that's the number, it's right around there. You're going to see basically a 10-to-1 ratio. So the difference between this conformation, one second, I'm going to die. Thank you. Sorry, Zoom, for the half cough in your ear. So the difference between this conformation and this, basically, it's 100 of these for every one of these, if you were to like take a picture, right? Roughly. And then same for this conformation versus this one. You get roughly 100 of these, maybe 1,000 to every one of these that you get, right? So if we can draw the right conformation that minimizes A13 and A12 strain, we can see, okay, if these groups weren't methyls, if this was a tert butyl and a methyl, right, you'd be like, oh, the tert butyl group was above the double bond, the methyl group's below, the methyl group's smaller, so my reagent's probably going to come from the side of the methyl group as opposed to coming from the side of the tert butyl, right? So if we can draw our conformation that gives us the lowest A13 strain, we can then use that to predict which side of the double bond is going to be open. And then that's going to let us predict which side our reagent comes from. So how can we do this? right? So how do we minimize A13 strain? So one, you want to arrange the groups so they kind of bisect that hydrogen at A2, right? So to minimize the A12 strain, you want your groups above and below that. Right? You want whatever you've deemed your smallest group needs to stick inside towards the double bond. So when there's a hydrogen, you want to stick that hydrogen inside and have it basically line up with the double bond, right? And then you want to add your remaining groups to the allylic carbon and maintain your stereochemistry. So what I do is I'll figure out if this is R or S. Then I'll put the hydrogen inside and then put the other groups on and make sure that it matches that it's still R when I'm done, or still S when I'm done. That way now I can say, okay, I have phenyl above, methyl below. Phenyl is going to block the top face, so my reagent's going to prefer to come from the bottom. So I've got this one drawn here, but let's actually kind of do it. All right, so we have this, right? So the first thing I want to do is I want to figure out, is this chiral carbon, is it R or is it S? So I will leave this task to Alphonse and the people of Zoom. Again, I have the chat window open, so if you just feel like I read something where they're like, Zoom chat is great, it lets people interact without calling attention to themselves. So I have Zoom chat open. If you'd like to interact and not call attention to yourself. I think it's R. Let's see here. We'll say the phenyl is 1. This is 2. That's 3. It looks like it's S, but the low priority group points at you, so it's R. So now we know that when we draw the other structure, that we need to have the groups be, we need to have that end up being R, right? That's our check, is we can check to make sure, like, hey, is this R when I'm done, right? So there are a couple different ways you can draw this. So first, I'll draw it like I have it on the slide, where the way I'm drawing it on the slide is, usually we draw double bonds, where we're looking at from the top down, right? So the way I have this one here drawn is I'm looking at it from the top down, where I've put all the carbons in plane. You can think about it, instead of looking at it like this, right, where here's my thumb, I could tip it, I shouldn't use my thumb, or the thumb will be away from you, right? Now this group's on a dash, right, because it's pointing away from you, so I've tipped my double bond from being in plane to now I'm looking at it from the side. So instead of looking at it from the top and bottom, you're looking at it from the side, so now that group is back. But what I can do is I can turn it so I can say, hey, this methyl group is pointing at me, right? So I've tipped the double bond, so we'll use this hand, right, because my thumb. Right, now I've tipped it, so now my thumb is pointing towards you, right? So that would put that group forward on a wedge. And then this group, since it's on the same side, will also be forward on a wedge. And then I'm going to stick the hydrogen inside, right? So now I'm looking at it from the side, hydrogen's in, and then I've got to put my phenyl group and my methyl group on, right? And I can say, I can angle my phenyl group up, and I can angle my methyl group down. So now they are splitting this hydrogen, right? One's above that hydrogen and one's below, right? Because they're all on the same, all of these are all in the same plane, right? They're all in the plane sticking out at you. So I have the phenyl above it in the hydrogen below it, or the methyl below it. Right, now let's check, is this the right stereochemistry? Right, so you can go with still 1, 2, 3, right? And it's a little hard to see, admittedly, right? But you could turn, and this is 4, right? Imagine putting yourself in a perspective where you could go phenyl is here, right? You're like phenyl, double bond, methyl group, and the hydrogen's away from you. So basically you're kind of standing over here and looking at it. So you can go phenyl, phenyl, methyl, and that would be R. You see that? Kind of. Let's see if my left AirPod is now charged. We could hope. Okay. Well, I was trying to be quiet, and then I just dropped my headphone, so I probably just deafened like 4 people. So sorry. Okay, it didn't like fall underneath the lectern. Right. Another way you could draw this, right, that might be easier to see is, right, you just leave it in the regular perspective that you do it in, right? You could draw it like this. You could stick your hydrogen in plane and then say like, okay, phenyl group is on the wedge, methyl's on the dash, right? Now you still have to check if this is R or S, but then you could use the same trick that we used in organic 1, where you would redraw it, leave your phenyl group up. That's not even letters. Leave your phenyl group up, hydrogen back, methyl, right? Redraw the stereocenter and say like, okay, this is 1, 2, 3, 4. This is S. I switched the hydrogen and the methyl group. So that means the thing I started with was R. Right? Remember the redraw it, you make the enantiomer, then you switch it back. Right? So here, again, this is easy to see that your phenyl group is above your methyl group is below. The open face is from the bottom, right? Because phenyl is bigger than methyl. So phenyl is basically blocking the top side of the molecule, and your reagent or whatever you're adding to that double bond is going to come from the bottom because that face is more open. So if you have a pi system, or if you have an allylic chiral carbon, if you can draw the conformation that minimizes A13 strain, right, that's going to tell you which face is open. Right. So what we need to do is we can use these 2 examples here, right? And you can see that the chiral center, even though they're not 100% the same, right? You've got this methyl group and then this methyl group, like these 2, furyl versus CH2O benzyl, aren't the same, but you change that chiral center and you change the stereochemistry you get for your product, right? Here my oxygen is back. Here my oxygen is up. Sorry, I don't have the ratio for this one down here, right? But so just changing this chiral center, changing the allylic chirality, changes which face of the double bond you approach from. All right, so let's try to actually draw these like reactive conformations, right? So we have this, and looks like I have Parkinson's, but whatever. So first thing you want to do is you want to assign R and S, or R or S. So you have a frame of reference, something to anchor you when you draw your other conformation. So this chiral center here, is it R or is it S? What I will say though is we'll say that the furan is highest priority. Just make sure that we're all on the same page. I do agree that this is S, 1, 2, 3. Looks like it's R. Low priority group points at me, so it's S. So cool. So now we know it's S. So now when we go to draw our structure, when we go to draw our conformation, we don't have to worry about, we can just make sure that we keep everything the same. So we want to put our hydrogen, if we draw it this way, we want our hydrogen to be in plane and eclipsing the methyl group on the double bond. So we want to have it like this, right? So what you can do that might make your life a little easier, right, is imagine that you're just turning this chiral center, right? So if you imagine that you take that and you twist it, it puts the hydrogen in plane, right? So you're twisting the hydrogen away from you, right? So it's currently forward, and you're grabbing it and you're turning it so it goes back. So when that happens, right, I don't have enough fingers, right? So let's say that this is the hydrogen, right? This finger right here, this is the furan, this is the methyl group, right? We'll do it down here. When I turn the hydrogen to put it in plane, right, the furan comes forward, the methyl group stays back. So for alphons, right? So hydrogen, furan in plane, methyl group. When I turn it, now the hydrogen's in plane, furan came forward, methyl group stayed back, right? It was just down and back before, now it's up and back, right? So what that's going to do is it's going to put our furan, apparently make it blue. Going to put our furan up, and it's going to put our methyl group back. Right, so again, just looking at it, you can say, well, the furan is bigger than the methyl group, so the furan is going to block the top face of my molecule. So my reagent, my boron, is going to come from the side of the methyl group, right? And so that's going to lead to, they use B2H6, which is just the dimer of BH3, right? You're going to end up with H, this, and then I guess there's going to be an oxidation, but again, I just wrote what was in the review, right? Oops. So that's going to put your hydrogen, your OH, sorry, hydrogen, you're going to move for a second, right? That's going to put your OH on the same side as that methyl group, right? Because it's coming from the same side that's open. That's going to put the hydrogen that you add on the same side as the methyl group, because it's a syn addition. The hydrogen and the oxygen that you add come from the same side. That's going to push the methyl group forward and then give you O-benzyl, right? So you would predict from minimizing the allylic strain in this reaction, or in this molecule, that you would have your OH on the same side as the methyl group. Right. Also, we just kind of glossed over that I am 100% cool and right. 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 If we then switched our groups, you'd end up with this being S. Right. So if we ended up with, we did it like this, H is back, double bond, 1, 2, 3. This looks like this is R, so that means the thing we started with was S. So I didn't screw up the stereocenter, right? Because I just twisted it. So like you can check. That's why it's important to figure out the stereocenter of your starting thing, so that when you do your allylic carbon, you can check it and be like, oh, I started with something that was S. I got something that was S. I didn't mess anything up. So does this match what they got in the paper? And the answer is yes, right? OH is on the same side as the methyl group. So the furan blocked the top face, boron came from the bottom face. So I'm going to draw the next one here. We'll end on this. If I can slow down the thing. Right, so if we have this, wow, not even close to letters. Right, if we have that, right, this is going to be 1, 2, 3. Or no, wait, no, it's going to be this way. 1, 2. Now, I want to tell you a secret. When you're doing this, where you just need the R and S, not to like say definitively this is R or this is S, when you just need it to make sure that your stuff matches, you don't actually have to do it right. Right? Right? Let's say this was actually supposed to be 2 and this was supposed to be 1. As long as you were consistent for the stereocenter that you said here and the one that you draw, which one was 1 and which one was 2, if they match, you're still good. So you don't have to expend too many brain cells. So what is this going to be? This one's easy, right? Should just be R. Right? Same thing that we did before. Now we can take this and put the hydrogen in plane. To put the hydrogen in plane, right? That meant that we had to turn we had to take the hydrogen was back, and so we turn it towards us, which is going to put the methyl group up and the O-benzyl back. Right? It turns, hydrogen is back away from us, and we turn it so it comes towards us. The thing that's forward stays forward, the thing that was in plane goes back. We can check to make sure I didn't mess up. It's always important. right? 1, 2, 3. This one you can kind of look down on, and it's R. But if you want to switch stuff, just to make sure, right, you could say, what if I had O-benzyl in plane, this up, hydrogen back, 1, 2, 3, 4. Oops. This is S, which means what I started with was R. So we know that this is correct. This one's a little bit harder to kind of definitively say which one's bigger because the size, right? This side is going to be the bigger side, but it's really far away from the chiral center, right? It's like a methyl versus CH2. Well, those are pretty close to the same size. Like the big difference, the benzyl is really far away, but it still kind of carries over. So we'll start here on Thursday. This means I don't have to make slides between now and then. Yay. Because I can make your test. Extra yay. So I think we'll be good. We'll stop here. We'll pick up here. We'll make sure that what we predicted is what shows up in the actual paper, and then we'll go from there and look at some examples.